typically looking at regional fields. And the reason is that we can do gravity um, relatively cheaply by setting out a gravimeter at a point and moving it along. You can go on to the USGS and you can find gravity maps of the entire United States and even the world. There has been a kind of a sea change in gravity lately, and we'll be talking about it probably toward the end of the class, but what we're able to do now for a fairly significant cost is actually run gravity from ships or from airplanes. And you can imagine if you're trying to measure the weight or the spring displacement of an object very carefully, that the acceleration of an airplane would really cause that measurement to be noisy. Whereas if you sit it quietly on the ground, it's much less noisy. But we've developed processing and analysis techniques that, as long as you're not too noisy, you're not flying in a thunderstorm, can actually do these gravity measurements from an airplane and cover huge swaths of land in a relatively short period of time. Yeah.
You didn't say anything about gravity from satellites.
That's another thing, yeah. Yeah.
That was really interesting.
That's very interesting. And the satellites are actually, they don't really, because they're in a vacuum, they don't have the air turbulence that's going around, although they are relatively far away from the objects of interest. Yeah, we're going to talk about both of those. We're not going to use them. We're not going to fly. We're not going to take a rocket up in space and collect any data that way, but I will show you a gravimeter. So in a regional sense, what we're looking for is basement structure. Sometimes we're looking at lithosphere and mantle structure, isostatics anomalies associated with varying thickness of the crust, and obviously density anomalies in large areas that are related to any of these things. For basement structure, that's a huge one in understanding the generation of hydrocarbons. It's also very important in understanding the geologic history of a particular basin or area. Lithosphere and mantle studies and isostatic anomalies are more academic than commercial. Locally, we can look at oil field processes. One example is displacement of the surface, which will show on a gravity survey, or what's called a tilt meter survey, which is a kind of a combination of gravity and very low frequency seismic. It's used often in shallow void detection, running gravity surveys over areas where you have voids. You can find tombs, open tombs in some cases, or more dense areas, tunnels, solution cavities, and mine shafts. Okay, so the first thing we've got to know about gravity is that what we're really measuring in gravity, if we've done all our corrections appropriately, and we'll talk about what those corrections are, is we're measuring the density of the material, basically kind of in a tube down from the surface of the Earth all the way to the center of the Earth. And as we'll see, you're most sensitive to the materials that are closest to your sensor, and you're less sensitive to the materials that are farther away from your gravity gravimeter. So these are just some different kinds of densities for different rocks and rocks. So coal, real not dense. Soil, 1.5 to 2 grams per cubic centimeter. You go up to limestones and shales, you're looking at 2.4 to 2.9 for lime and 2.4 to 2.6 for shale. So once you get into rocks themselves, you can see that the variation in gravity properties is relatively small. Okay? So you've got to have a very sensitive measurement to distinguish between different lithologic types. What you can probably do here, if you could measure the difference between, say, a limestone and a basalt. Okay, the limestone is somewhere about 2.6. The basalt is somewhere between 2.8 to 3. So you're looking at maybe a 10% difference in the gravity between those two types of rock. When you get into various things like iron, hematite, you see a huge, or not huge, but a factor of maybe 2 or a little bit more than that difference in gravity. So this explains kind of why you need such sensitive equipment to measure the difference in these properties. Obviously, if you're looking at an interface between soil and rock, you've got roughly a factor of 2 difference. So measuring measuring large contrasts is going to be is easier. And obviously, when you have holes in the earth, your density, your air density is basically 0. So that's why gravity works in a situation like that. Okay, so here's an example of basement depth from a gravity inversion. And we'll talk a little bit about how gravity is inverted later on. In this case, we're trying to understand basically the transition between continental crust and oceanic crust. And the depth here represents the depth of the basin, so you can see that basically